Welcome back to the May exams, TZ2 IB Chemistry walkthrough for paper 1A HL. We're going to keep going with questions number 16 through 20. By the end, we'll be halfway through. Yippee! So question number 16 has to do with the electron configuration. And this is a mistake that you all make very frequently, all the time. There's two things that you all do and that they're trying to trick you to do. This question is very purposeful, okay? It's targeting the two things you all do all the time, okay? So the first one is the fact that it's the electron configuration of an ion of chromium. Chromium is one of the two exceptions they ask about literally every year. I'm not kidding. Every year. Every single year. It's copper and chromium. They ask about one or the other every year. Okay. And so if you look at your periodic table, I'm going to go over to the data booklet. We're going to scroll. There we go. If you look at your periodic table, so chromium is there. And so normally you want to think that it's electron configuration. We're going with the noble gas configuration because we're not going to write all of that. Is you would think that it would be 4s2 and then 3d, 1, 2, 3, 4. Okay. The thing about the d orbitals, it doesn't like to be it likes to be either halfway full or fully full. It's just very nice. Okay, it's a very stable configuration. Is D5 and D10 are very stable. And so whenever it's at 4 or it's at 9 for copper, is it will steal an electron from the 4s2 orbital and become instead 4s1 3d5. Okay, just because its stability is so much higher, this is very energetically favorable to happen. Okay, and so because of that, so chromium not ionized is 4s1 3d5. Okay, so we're gonna go ahead and write this over here. It's just chromium neutral is 4s1 3d5. Okay, the next mistake that you all make is that whenever you're doing ions of transition metal element, regardless of if it's this weird exception or not, the transition metal elements is it goes from the s orbital first. Like we already worked so hard to get that d orbital subshell stable. Okay, why would we immediately make it not anymore? Like, okay, we're gonna take from the s first. Like we already took from s to make our d5, so obviously that one's easier to take from. Okay, and so we're going to take one from there and then one from d orbital because then it's empty. So our Cr2 plus will be 3d4. Okay, and so that makes the C the right answer for question number 16. Okay, so question number 17 has actually shown up on a past IB exam before. I will put a screenshot of that question here. The only thing that differs is that it's fluorine instead of chlorine, and for some reason they decided, I don't know, maybe it would be funky fresh if they just tilted the rings. I don't know, like that would make a difference. But either way, this question has been done before, and I will explain why I think it's technically out of the subject guide, and I have beef with the IB for this. But either way, we're gonna solve it. Okay, and so it's which compound shows cis-trans isomerism. Okay, and so normally we're looking for where if you have a double bond, so normally you're looking for a double bond. Is normally you have a double bond, and you need that your first carbon has two different groups, and then your second carbon also has two different groups. If either carbon has the same groups, then it's not cis-trans isomerism, okay? We're going to ignore A and B for now because we're going to get there. We're going to look at just C and D. So C and D is this first carbon has H2 out of the running, same group. So C is out. Meanwhile, D, you've got CFH, okay? Carbon 2, CF2, out of the running, okay? And so D is out of the running. Now, we're going to look at A and B. So you may think, and the IB wants you to think, they're tricking you. They want you to think, oh, it's A because of there's a double bond, and technically there's two different groups on each atom. Technically, okay? But what you need to do is think about technically what causes cis-trans isomerism. So normally what causes cis-trans isomerism is that normally you have in a single bond, just a sigma bond, there's free rotation about the bond. Okay. Meanwhile, when there's a double bond, it locks it into place. There's no free rotation. So it either has to come from one side or the other. Okay. That's kind of the big thing. Okay. And so That's what causes cis-trans isomerism. When you're looking at A, if you have a molecular model kit, get it out. I don't have mine. Mine's at the office at school, but I'm going to show Mulview to give a better idea. So with A, you have that difluorocycloalkene, okay? And so if you go, and this is the wrong one, where this one over here, there we go. This is the alkene version. So if you look at, I can't do my little laser thing, but if you look at the double bond and then the two fluorines, the greens, okay, is because there's that double bond there, it's kind of like double locked in place. Is normally you're kind of only locking like one orientation. Now like it's like more things are locked, okay? There's literally no choice but for these fluorines to be on the same side. Cis is the only possible confirmation. Trans is not. If you want to get technical, technically trans theoretically could be possible, but it would be a very strained formation that's just not energetically favorable. Okay. That's a higher level than this though, because even though we do cis-trans isomerism, we don't go over shared conformations or any of that. So that's kind of just above. So we're going to stick just to the basics here and ignore that on a technical note. And so there's literally only the cis conformation possible. Therefore, it does not show cis-trans isomerism. Meanwhile, with that alkane version, you can see here, will it load? Will it update on my screen as a treat? Screen, there we go. Okay, so you can see this now alkane version. If you look at your fluorines in this kind of view, you have them as trans. However, because you have that hydrogen, it could go either way, right? The rest of the ring is locked in place though by the fact that it's a ring. Whenever you connect all of those carbons together, you have that strand that's similar to an alkene, does lock the conformation in place. So there is no free rotation. Okay. And so that is why the answer is B. Okay. The answer is B because it does have that locked from the ring, but there still is room for cis or trans. A kind of has double locked, which means only the cis confirmation is possible. Okay. And so this is also a very specific aspect of the subject guide. I'm going to put it right here, a screenshot. We love the subject guide. It's the Bible. Is it says that students should be aware of C3 and C4 cycloalkanes as an additional thing they need to know for cis-trans isomerism. This is where I have beef with the IB. This is technically C6. This isn't C3 or C4. What? What the heck, IB? Anyways, so yeah, they've done it twice now. So there's that. But the answer to this one is B because of that. Also, I just realized before we move on to question number 18, I did want to point out that what cis-trans isomerism like means and how it's denotated in cycloalkanes is usually it's just up down, right? So for cycloalkanes, it actually is with wedges or dashes. So for instance, with like B, like if you had both of these as wedges, is that would be trans. Meanwhile, if you had boop, a wedge and a dash, a combination of the two, that would be trans. And I actually had a brain fart. Is that first one be cis? My bad, my bad, my bad. Listen, I don't know words. Cis. So same side, cis, opposite sides, trans. Normally you just go as up and down, and wedges and dashes are only used for chirality or that kind of 3D notation. But for cis trans isomerism with cycloalkanes, you do use wedges and dashes to denotate that. I think this is important to point out because if there is ever, and there have been questions about stereoisomers, that have to do with cis-trans isomerism with cycloalkanes, that would be how you would denotate that. So, yeah, just a note before we move on. Okay, now time for question 18. Now that that's out of the way, this question is saying, what is the correct interpretation of this energy profile? I feel like this has shown up before. I don't know. Maybe a slightly different format, but it feels like it's shown up before. But the big things to remember with this one is the first part is the react relative stability. God, is the relative stability, and so things that are lower energy are higher stability. Okay, so lower energy, higher stab stability. Stab. Okay. And so whenever you're looking at the reactants versus the products, the reactants, this axis is showing the energy. So the reactants are lower energy than the products. So the reactants are going to be more stable. So yay, stab. Okay. And so for this first kind of column, reactants more stable than the products, that would be right, taking C and D out of the running. Okay. Meanwhile, that next column, that temperature of the surroundings, not the system. Okay. And so you have to see whether this reaction is endothermic or exothermic. And so since the products are higher energy, that is going to make this reaction endothermic. If you forget, like I just remember the shape of the profile. Like I don't know why. Like the way that I do it, I remember that like that is endothermic, but I remember exo because it kind of looks like a sneeze. I don't know how to justify it. I genuinely don't like. I feel like choo. Don't know. I don't know. Okay, that's how I remember that. And if it's not the sneeze, then it's endothermic. But if you forget on an exam, you also can know that the difference between the products and the reactants is the overall enthalpy. And so products like high minus low has to be positive. Like that's just how math works, right? And so if the reactants were higher, then it would have to be negative because products, it's always your overall is products minus reactants. Does that make sense? I hope it does. But yeah, so this is endothermic, which endothermic means that it needs energy. Okay, is it needs energy. And so because it needs energy, it takes it, it robs the surroundings. The surroundings is being robbed. Okay. The system gains energy. Okay. And so the temperature of the surroundings is going to decrease because its energy has been stolen. It's been robbed. So decreases, decreases. Boom. So this is going to be A for question number 18. Okay, so question number 19. This is asking about what the standard enthalpy change is according to this calorimetry data. You just need to know how to use your data booklet, math, and your calculator because sometimes y'all just be inputting stuff in your calculator wrong. Weird. Anyways, so you're gonna look at your data booklet. You're gonna use section number 1, and you're gonna use the funny formula Q is equal to MC change in T. Wicka wiki wa. Okay, and so we're going to use that to solve for Q, and then we're going to use this other equation to solve for delta H. I don't know why it's not a data booklet, and I'm not going to lie, I actually didn't notice this until I was taking this exam myself. I was like, wait, is that not a data booklet? That explains why students keep forgetting it. I feel bad because I've like written on students' exams. Look in your data booklet for this equation. Anyways, so we have Q is equal to MC change in T voice crack, and then eventually we will use that the delta H is equal to negative Q over N. Okay, and so first we need to see what is what, and so for M, it's our mass, and we have the mass of water as being 200 grams. And I always like to write the units because you can check your work by making sure your units cancel out. And this one has units, things that trip students up. So write them out. I swear to God. Or be like me, and whenever I took this myself, because I know whenever I've taken exams myself under time conditions, yeah, it's hard to write out the units. Just do them for these types of questions, okay? And if not, whenever you check your work, rewrite it with your units to check yourself. Anyways, so we have this 200 grams. Our C is this 4.18 joules grams Kelvin. Okay, our change in T is the difference between 25 and 21. So it's going to be 4 degrees. Uh, any degree change in degrees Celsius is the same in Kelvin. So we're going to say 4 Kelvin. Cool. And so whenever we put that into our calculator, we end up getting this 3,344 joules. Cool. And so then if you go over to your delta H, you'll put that at negative 3,344 joules divided by our number of moles, which it says up here is 0.110 mole. And so whenever we put that in our funny calculator, we end up getting this, where is it? Negative 30,400 joules per mole. However, our answers all over here are all in kilojoules per mole. And so joules is always bigger, so we just need to move our decimal point 3 places to the left. Okay, so that is equal to 30.4. kilojoules, and negative, don't forget the negative, kilojoules per mole. So negative 30.4 kilojoules per mole, which gets us to be that the answer is B for this question. Okay, question 20. We got this last one for this video is literally just balancing. Very easy, very nice, and nice break. And it's specifically for a combustion equation, and we're looking for the coefficient of oxygen. Okay, and so I always like to do my balancing equations a certain way. Is I always just list the atoms for reactants and products on each side, and then I just balance them in order. Okay, so I count, recount, whatever. So currently, at the beginning, before we do anything, our number of reactants are carbons. We've got 2, hydrogens, we've got 6, and then oxygens, we've got 3. Our products, we've got 1 carbon, 2 hydrogens, and 3 oxygens. We're going to balance our carbons first, and we just need to balance our products to become 2. Only one thing in our products contains hydrogen, CO2. So we're just going to make that, boom, 2. Recount, we've got 2, and now we've got 4, 5 oxygens. Same thing with our hydrogens. Only one thing in our products contains hydrogen, which is H2O. And so we need it to become 6. And in our product, H2O, we have H2. So we're going to 6 divided by 2. That's going to give us 3. So we're going to put 3 right there. So now we've got our nice 6. And then now we've got 3, 4, 5, 6, 7 oxygen. Okay. Now to make our oxygens match the reactants, now our reactants is we have currently 3. We have 1 compound as O2. We're going to use that and balance that. But our other compound, C2H5OH, has 1 oxygen. So already 1 is accounted for. We need 7. So now we just need to find 6 more. Okay. Our O2, 6 divided by 2, 3. So 3. And so now our oxygen is 7 as well. And so our coefficient for oxygen is 3. So that makes this answer C for 20. And now you are halfway done with this godforsaken May exam. Pat yourself on the back, give yourself a thumbs up. Yay, good job. And now continue to do the rest.